Database management systems. Introduction. Welcome to database management systems. A database management system, or DBMS, is software that stores, organizes, and manages data efficiently. Almost every modern organization depends on databases. An organization can be anything: a small business, a large corporation, a university, a bank, a government, even an individual managing large amounts of information. A database system provides a collection of related data programs to process the data, a convenient and efficient environment for using the data. Why databases matter. Databases are everywhere. Banking. When you use online banking, UP, Paytm, Google Pay, or similar services, large databases are working behind the scenes to track balances, transactions, and account information. Reservations. Airlines, railways, and ticket booking systems rely heavily on databases to manage seats, schedules, and bookings. Universities, educational institutions use databases for admissions, registration, examinations, grading, timetables, student records. E-commerce. Online stores such as Amazon and similar platforms depend on databases for product information, orders, payments, inventory, customer accounts. Other industries' databases are also essential in manufacturing, human resources, healthcare, travel, logistics applications. You may not think about many services that don't seem like database applications actually are. Examples include email systems like Gmail, social media platforms, messaging applications, contact management systems. These services constantly store, retrieve, and update information using databases. Because databases are used almost everywhere, skills in database design, database programming, database administration are highly valuable across the technology industry. Problems with simple file systems. Before modern databases became common, organizations often store data directly in files. Examples include text files and CSV files. CSV stands for comma-separated values. While file systems are simple, they create several problems. Data redundancy. The same information may be stored in multiple files. This leads to duplication and waste storage. Data inconsistency. When the same data exists in multiple places, updating one copy but forgetting another creates inconsistencies. For example, a customer's address might be updated in one file but remain outdated in another. Difficulty accessing data. Data stored in files is harder to search and process automatically. You often need custom programs or manual effort to retrieve information. Data isolation. Information may be spread across multiple files and formats. This makes integration difficult. Integrity problems. Many systems require rules to be enforced. For example, a bank account may require a minimum balance. A file-based system must remember and enforce these rules everywhere they are needed. This becomes difficult and error-prone. Atomicity. One of the most important database concepts is atomicity. Atomicity means either an entire operation happens or none of it happens. Consider transferring 100 rupees from one account to another. The system must debit 100 rupees from the sender, credit 100 rupees to the receiver. Suppose the first step succeeds, but the system crashes before the second step. The money disappears. To prevent this, databases treat the transfer as a single atomic transaction. Either both steps succeed, or both are cancelled. Concurrency. Modern systems are used by millions of people simultaneously. For example, if only one train seat remains available, two users might try to book it at the same time. The database must ensure that only one person receives the seat. Handling many users safely and fairly is called concurrency control. Security. Databases must also protect information from unauthorized access, identity theft, data leaks, malware attacks. Security is a major responsibility of every database system. Why use a database? Databases solve problems related to redundancy, inconsistency, data access, integrity, atomicity, concurrency, security. This makes them far more reliable than simple file-based storage. Prerequisites for studying databases. To understand database systems well, you should be comfortable with several topics. Set theory important concepts include sets, membership, subsets, supersets, power sets, universal sets. Operations include union, intersection, complement, difference, Cartesian product. You should also know De Morgan's laws. Relations and functions. Understand ordered pairs, binary relations, domain, range, image, pre-image. Properties of functions. Propositional logic. Know concepts such as truth values, truth tables, conjunction, disjunction, negation, implication, equivalence, predicate logic. Be familiar with quantifiers. Examples: all humans are mortal. Every child has a mother. These involve universal and existential quantification. Data structures. Important topics include arrays, list, search trees, binary search trees, balanced trees, B trees, hashing, hash maps. Many database internals are built on these ideas. Python programming. Python will be used extensively. You should be comfortable reading and writing Python code. Additional database-related Python features will be introduced during the course. Helpful but optional knowledge. The following topics are useful, but not strictly required. Algorithms, especially search and sorting. C programming, useful for understanding low-level implementation details. Object-oriented programming concepts from Java, C++, and object-oriented design often overlap with database design. Course structure. This is a 12-week course. There are approximately 5 modules per week, 60 modules in total. Weeks 1 to 8 focus on database application programming. These skills are widely used in industry and provide strong employment opportunities. Weeks 9 to 12 focus on database administration, database design, advanced database topics. These roles are often more specialized and highly valued. Textbook. The recommended textbook is Database System Concepts by Abraham Silberschatz, Henry F. Koth, and S. Sudarshan. The course is based primarily on the 6th edition, though later editions can also be used. Key takeaway: database systems form the foundation of modern computing. They power banking, education, e-commerce, communication, transportation, and countless other services. By studying database management systems, you learn how to store, organize, secure, and process information reliably at scale.
Welcome back to Module 2 of the Database Management Systems course in the IIT Madras Online BSc program. In Module 1, we took a basic look at how databases are present in almost every aspect of our lives. Whether we notice it or not, databases are used everywhere. Even something as simple as making a phone call relies on large database systems. These systems track phone numbers, locations, network connections, towers, base stations, and much more. In modern life, it is essentially impossible to function without databases. In this module, we go deeper into the need for database management systems from a historical perspective. We ask a basic question: why do we even need DBMS? What did humans do hundreds of years ago, or even just a few decades ago, before modern systems existed? And how have these systems evolved alongside both technology and society? On one side, technology keeps advancing rapidly, making new capabilities possible. On the other side, society is also changing, producing new kinds of data needs. For example, during the pandemic, applications like SETI were used to track health conditions and proximity risks. This required large-scale data collection, location tracking, and correlation across millions of users. Similarly, the CoWIN system managed the entire vaccination program of a country. It tracked who was vaccinated, where, with which vaccine, which dose it was, when the next dose was due, and also generated certification records. Systems like these were not possible even 10 years ago because the required infrastructure did not exist at scale. To understand how we reached this point, we take a historical view of data management. At its core, data management is about several key needs. First is storage. We need to remember information such as money, inventory, employees, or records. Second is retrieval. Stored data must be accessible when needed. Third is transactions. Real-world changes must be reflected in data, such as buying a product and transferring ownership. Fourth is auditing. We must be able to trace what happened, detect errors, verify compliance, and prevent fraud. Fifth is archival storage. Some data must simply be preserved for long-term future use. These needs apply whether the system is for an individual, a small business, a large corporation, or even a global organization. Historically, there have been two main approaches to handling data. The first is physical data management. In this approach, information was stored using paper records such as ledgers, journals, and files. This practice, often called bookkeeping, has existed for centuries. Over time, systems like file cabinets helped organize physical records more efficiently. However, physical systems have major limitations. They are prone to damage from fire, humidity, insects, and general wear and tear. They do not scale well. A small shop may manage records for hundreds of customers, but not millions. Security is weak and depends heavily on physical protection. Retrieval is slow because records must be searched manually. Consistency is also difficult, as updates may be missed or duplicated. In the late 19th century, improvements began with better filing systems and early mechanical ideas for storing information. Later, punch cards inspired by weaving machines were used for early computation and data storage. These developments laid the groundwork for electronic systems. The second major approach is electronic data management. This began in the mid-20th century with computers. Early systems used punch cards, magnetic tapes, and later magnetic disks. Programming languages like COBOL were developed for business data processing. Early data models and systems like Codicil also emerged. In the 1970s, relational databases were introduced, which became a major turning point. In the 1980s, SQL became an industry standard, and database systems became more widely adopted across organizations. Around the same time, spreadsheets like VisiCalc appeared, which later evolved into modern tools like Excel and Google Sheets. In the 1990s, the Internet expanded databases to a global scale. In the 2000s, e-commerce systems drove massive growth in data storage and processing. At the same time, there was increasing demand to handle unstructured data such as images, videos, audio, and natural language text, which led to NoSQL systems. In recent years, data science has emerged on top of these systems, relying heavily on databases for storage, retrieval, and processing of large-scale data. Modern electronic data systems are evaluated based on several important factors. They must be durable so data is not lost. They must be scalable to handle anything from small to massive workloads. They must be secure, though the level of security depends on the application. They must allow fast retrieval of data. They must ensure consistency, so data remains correct after transactions. They must also be efficient in terms of time, storage, maintenance, and cost. Even today, simpler systems like spreadsheets and flat file systems are widely used. However, they have clear limitations in scalability, consistency, security, and multi-user access. This is why dedicated database management systems are necessary. Looking at the history of DBMS, early systems used tapes and punch cards in the 1950s and 60s. In the 1970s, relational models were developed, especially through the work of researchers like Ted Codd. The 1980s saw the rise of SQL and enterprise database systems. In the 1990s, the Internet made databases distributed and global. In the 2000s, systems for unstructured data and massive-scale storage emerged, such as those used by large Internet companies. Today, databases form the foundation for data warehousing, data mining, and data science. Modern systems like Oracle, SQL Server, MySQL, and PostgreSQL continue to evolve, along with large-scale distributed systems used for big data. In summary, database systems have evolved from simple physical record keeping to highly scalable, secure, and distributed electronic systems that power almost every digital service today. Thank you for your attention. Here's the cleaned, continuous audio version of Module 3. Welcome to Module 3 of the Database Management Systems course in the IIT Madras BSc online program. In the previous module, we discussed the evolution of data and record management systems, moving from physical systems to different generations of electronic systems. We also briefly introduced the history of DBMS. In this module, we continue that discussion, but from a slightly different angle. We now compare file-based data management systems with database management systems. To make this concrete, we use a simple case study. We consider a basic banking system where a user can open an account, transfer funds to another account, and view their transaction history. These are simple operations, but they represent the core of most real-world financial systems. The system has three main rules. First, if the account balance is insufficient, the transfer should not be allowed. Second, if the account numbers are invalid, the transaction should be terminated with an error message. Third, if the transaction is successful, a confirmation message should be displayed. We compare two implementations of this system. One uses a file-based approach with Python and CSV files. The other uses a database system with SQL. In the file-based system, we use two CSV files. One file stores account information, and the other stores transaction logs. In the database system, we use two corresponding tables, an accounts table and a ledger table. Now we compare how the same operations are implemented in Python versus SQL. In Python, a transaction function must explicitly handle everything. First, it opens the CSV files in read mode to load account data. Then it opens a ledger file in append mode to record transactions. These file operations must be done every time a transaction is executed. In contrast, in a database system, the setup is persistent. Once the database is running, the necessary connections and structures remain available. You do not need to repeatedly open and initialize files for every transaction. Next comes the balance check. In Python, you manually check whether the account has sufficient balance. In SQL, this is done using a query that retrieves the balance and compares it with the transaction amount. If the balance is sufficient, the system proceeds to debit the account. In Python, this requires conditional logic and manual updates to the data structure. In SQL, an update query directly modifies the balance in the database. After debiting the sender's account, the system credits the receiver's account and records the transaction in the ledger. In SQL, this is done using insert and update operations. A key feature in database systems is the commit operation. Until commit is executed, changes remain temporary. Once commit is called, the transaction is permanently saved in the database. Python file-based systems do not have this built-in mechanism. If a failure occurs after debiting one account, but before completing the transaction, the system may be left in an inconsistent state. The debit may have happened, but the corresponding credit and log entry may not. This leads to data inconsistency. In SQL databases, this problem is solved using rollback mechanisms. If a failure occurs during a transaction, the system can undo previous changes and restore the database to its original consistent state. Finally, in Python, after a successful transaction, files must be manually reopened and written to ensure the updated state is saved. In SQL, once commit is done, the system automatically handles persistence and cleanup. There is no need to manually manage file handles or write-back operations. This comparison highlights an important point. While file-based systems using Python can implement similar logic, they require significantly more code and manual handling. They are also more vulnerable to errors and inconsistencies. However, file-based systems still have use cases. They are suitable for small-scale applications where the number of records is small and strict consistency, security, and scalability are not critical. They are also easier to set up and require less overhead compared to full database systems. Database systems, on the other hand, are designed for robustness, scalability, and reliability. They support large-scale operations, concurrent users, structured transactions, and built-in recovery mechanisms. We can compare the two approaches across several dimensions. In terms of scalability, file systems struggle with large data and complex operations, while databases handle large-scale insert, update, and delete operations efficiently. In terms of structure changes, modifying a database schema is relatively simple using SQL, whereas file-based systems require significant code changes. In terms of performance, file systems may become slow as data size increases, while databases are optimized for fast query execution. In terms of persistence, file systems rely on manual write-back operations, while databases ensure persistence automatically. In terms of robustness, file systems are vulnerable to data loss and corruption, while databases provide backup, recovery, and restore mechanisms. In terms of security, file systems usually rely on basic operating system permissions, while databases support multi-level, role-based access control. In terms of programmer productivity, database systems reduce the amount of code and complexity required, making development and maintenance easier. In terms of cost, file systems are cheaper and simpler for small applications, while databases involve higher setup and maintenance costs, but become more efficient at scale. In summary, file-based systems are suitable for small, simple applications, while database management systems are essential for large-scale, reliable, and secure data management. This concludes Module 3.
Here's Module 4 rewritten as smooth audio narration. Welcome back to Module 4 of the Database Management Systems course in the IIT Madras BSc online program. In the previous modules, we discussed why database systems are needed, and we compared database systems with file-based data handling solutions. We also looked at their advantages and limitations. From this module onward, we begin introducing the basic concepts of database systems. This module, and the next one, focus on the fundamentals of DBMS. Our goal here is to become familiar with the core terminology, basic data models, database languages, and the foundations of database design. First, we begin with a key idea, levels of abstraction in a database system. Unlike simple systems like spreadsheets, where you usually see data in only one form, a database system organizes data into 3 levels. The first is the physical level. This describes how data is actually stored inside memory. It is the lowest level and deals with bits, bytes, and storage structures. This is what is physically written to disk or memory. The second is the logical level. This describes what data is stored and how it is structured. For example, an instructor can be represented as a record consisting of fields like ID, name, department, and salary. Each field has a specific type such as string or integer. This level is used by database designers and engineers to define structure and relationships. The third is the view level. This is what the end user or application programmer sees. It provides a customized view of the data depending on the application. For example, one view might show an instructor's courses or student supervised, without showing sensitive information like salary. Another view might show only relevant fields such as name and department. Views can also contain derived data. For instance, instead of storing age directly, the system stores date of birth, and age is computed dynamically when needed. This allows different applications to use the same data in different ways without duplication. Importantly, while there is only one physical and logical representation of data, there can be multiple views depending on the user or application. Next, we discuss schema and instance. A schema defines the structure of the data. It describes how data is organized, similar to the blueprint of a table. For example, a customer schema might include fields like customer ID, name, account number, ATAR ID, and mobile number. An instance refers to the actual data stored at a particular moment. It is the real content of the database, like rows in a table. Instances can change frequently as data is added, updated, or deleted, while the schema remains mostly stable. If the schema changes, then all instances are affected. For example, adding or removing a field changes the structure of all data entries. This leads to an important concept: data independence. Physical data independence means that changes in the physical storage of data should not affect the logical structure. For example, changing storage hardware or file organization should not require writing the logical schema or application logic. This is similar to the idea of interface and implementation in object-oriented programming. The interface remains stable, while the internal implementation can change. Next, we move to data models. A data model is a collection of concepts used to describe data, relationships, constraints, and semantics. Different models have been used over time. The most important model in this course is the relational model. Other models include entity relationship models used in database design, object-based models, hierarchical models, network models, and more recently, models for semi-structured or unstructured data such as images, videos, and text. The relational model represents data in the form of tables, also called relations. Each table has columns called attributes and rows called tuples or records. This structure is simple and powerful and forms the basis of most modern databases. Historically, data models have evolved from simple hierarchical and network structures in the 1960s and 70s to relational databases in the 1980s, and later to graph models and NoSQL systems in the 2000s and beyond. Next, we discuss relational databases with a simple example. Consider tables like instructor and department, where each contains structured information about entities in a system. Now we introduce database languages. The first is Data Definition Language, or DDL. DDL is used to define the structure of the database. For example, creating a table with specific fields and data types is a DDL operation. The schema definition is stored in a system catalog called the Data Dictionary, which keeps metadata about all database objects. The second is Data Manipulation Language, or DML. DML is used to manipulate data inside tables. This includes operations like select, insert, update, and delete. These are used to query and modify the actual data stored in the database. SQL, or Structured Query Language, includes both DDL and DML features, and is the standard language used in most database systems. From a theoretical perspective, SQL is not Turing-complete, meaning it cannot express all possible computations that languages like C or Python can. Because of this, SQL is often combined with host languages like Python, Java, or C++ for complex application logic. In real systems, SQL handles data storage and retrieval, while a host language handles business logic, calculations, and application-level processing. Finally, we touch on database design. Database design is a complex task involving both logical and physical considerations. Logical design focuses on choosing good schemas how to structure tables and relationships. Physical design focuses on how data is actually stored and accessed efficiently. Good design depends on both business requirements and computational efficiency. There may be multiple correct designs, but some are better than others depending on the use case. As an example, combining instructor and department information into a single table may seem simpler, but it can introduce redundancy and design problems. Determining whether such a design is good or not is part of database design thinking. In summary, this module introduced the foundational concepts of DBMS, including abstraction levels, schema versus instance, data models, database languages, and basic ideas of database design. We will continue building on these ideas in the next module. Thank you.
Module 5. Audio Ready Script. Welcome to Module 5 of the Database Management Systems course in the IIT Madras online B.SC. program. In the previous module, we introduced the basic notions of DBMS, including terminology, data models, languages, and an overview of database design. In this module, we continue the same thread, focusing more deeply on database models, internal components of a DBMS, and a high-level view of database architecture. We begin with database design again. Database design has two main parts: physical design and logical design. Physical design concerns how data is actually stored on disk, including files, indexing structures like B-trees, buffering, and memory organization. Logical design, on the other hand, is about how data is structured: conceptualities, attributes, relationships, and constraints. Logical design is influenced by two major factors. The first is business requirements, what data the application needs, and what queries must be supported. The second is computer science considerations, how to structure data efficiently, including normalization and schema design choices such as whether to split or combine tables. Physical design is usually handled at an early stage and tends to remain stable. Logical design is more directly connected to applications. A key idea here is physical data independence. Changes in physical storage should not significantly affect the logical schema. Next, we revisit a design example involving faculty, departments, salaries, and department details. If all this information is stored in a single flat table, redundancy appears. Department data such as building and budget gets repeated for every faculty member in that department. This redundancy creates problems. It increases storage usage and, more importantly, leads to update anomalies. If a department budget changes, it must be updated in multiple rows. Missing even one update leads to inconsistent data. This is why such a design is considered poor. A better approach is decomposition into multiple tables, one for faculty and one for departments. The faculty table stores the department name as a reference, and the department table stores department-specific information. This removes redundancy and reduces anomalies. This idea leads into the broader principle of normalization, which will be studied formally later. We then discuss design approaches. One approach is the entity relationship model, which captures real-world entities, their attributes, and relationships in a diagrammatic form. The second approach is normalization, which ensures relational schemas are structured properly to avoid redundancy and anomalies. We briefly introduce extended data models. Object relational models allow attributes to have complex, structured values instead of only atomic values. XML is another important representation format, designed for hierarchical and semi-structured data, widely used for data exchange between systems. Next, we move to the DBMS engine, which has three major components: storage manager, query processor, and transaction manager. The storage manager is responsible for how data is physically stored and retrieved. It interacts with the operating system's file system, manages indexing, buffering, and efficient storage access. The query processor handles SQL queries. It parses SQL, converts it into an internal representation such as relational algebra, optimizes the query for efficiency, and generates an execution plan. It also uses statistics to improve performance over time. The transaction manager ensures correctness when multiple operations are executed as a single logical unit. A transaction may involve multiple steps such as checking balances, updating accounts, and committing changes. It ensures atomicity and handles concurrency so that multiple users do not corrupt shared data. We then look at internal system roles. End users interact through applications. Application programmers build those systems. Analysts optimize frequent or complex queries. Database administrators manage installation, configuration, backup, and recovery. Finally, we review database architecture evolution. Early systems were centralized mainframes. This evolved into client-server architectures, where applications act as clients and the database acts as a server. Later developments include parallel, distributed, and cloud-based systems. Modern systems also include NoSQL architectures for unstructured and semi-structured data. In summary, This module introduced deeper aspects of database design, redundancy and normalization ideas, extended data models, core DBMS engine components, and the evolution of database system architecture.